This video demonstrates the signal quality of the Analog Devices FMCOMMS11 eval board when using 5G cell phone signals. My name is Don Metzger and I'm with Quick Systems. The FMCOMMS11 board consists of an AD9162 DAC. This is a one-channel 16-bit DAC with sample rate up to 12 gigasamples per second. There's an ADL5240 amplifier and step attenuator in the transmit path. On the receive side is an AD9625 digitizer. This is a one-channel 12-bit 2.5 gigasample per second ADC. In the receive path is an HMC1119 step attenuator. The transmit output is looped to the receive input using a small cable. The host board is a Xilinx ZC706 with an Ethernet connection. The ZC706 is running Analog Devices IIO software. The FMCOMMS11 board has an input and output sample rate of 1.96608 gigasamples per second. This is the sample rate for 5G, so the board is set up ready to go for 5G signals. We'll send complex baseband IQ samples to the board and capture real valued samples, both at 1.96608 gigasamples per second. We will be using quick transceiver software from Quick Systems. First, we set the board type and connection parameters for the setup we are using. Next, we set the parameters for the FMCOMMS11 hardware. We will transmit at 400 MHz using 0 dB of gain. We will receive with 0 dB of attenuation and acquire 300,000 samples. Finally, for our transmit signal, we will use a pre-built 5G waveform with 240 kHz subcarrier spacing, 100 resource blocks, 16 QAM modulation, and transform precoding turned on. Hitting the Start button on the main toolbar gets things going. There are various views we get of the acquired data, including power versus time, average spectrum, spectrogram, and persistent spectrum. The absence of data in the constellation plot shows that the DMOD is not running. If we stop the program, we can see in the power plot that we are acquiring some reference sequences. The spectrogram also shows the reference sequences, but the DMOD is not locking on. The data coming from the system is real valued and is on a carrier frequency. The first thing that we need to do is to shift the received data from 400 MHz down to DC. We will do this using receiver waveform processing. Let's shift the acquired data by minus 400 MHz. This shift is done in software, not in the chip. After starting again, we see that the processing data is now at baseband. However, the DMOD is still not locking. The problem is the DC offset of the ADC. This small signal is keeping the correlation with the reference sequence from succeeding. To solve this, we will do a decimation by 2. The filter in the decimation gets rid of the DC offset, which has been shifted to minus 400 MHz, and allows the DMOD to lock on to the reference sequence. Now we see the received constellation and the EVM by subcarrier. We can also see the ESNO or EBNO or EVM in the results window. Let's increase the transmit power to get a better signal-to-noise ratio. We will set the transmit gain to 20 dB. The EVM by subcarrier plot has averaging turned on, so it will drift to its new value. We can speed that up by resetting the averaging. So, we can now see that the EVM is around 0.3% and the ESNO is about 50 dB. For a bandwidth of about 290 MHz, that's very good. Let's push the system a bit more. Let's use a signal with 240 kHz subcarrier spacing, 138 resource blocks, which is the maximum, and use 256 QAM modulation. When we run this signal, we get an EVM around 0.45% and an ESNO of about 47 dB. For an occupied bandwidth of nearly 400 MHz, Those are quite good numbers. If there's a board and signal type that you're interested in, and it's not already covered by another video on our channel, you can send an email to videos@quicksystems.com. We'll see what we can do about making that happen.